Hello everybody and welcome to the channel. So if you're studying civil or structural engineering or even just curious about how buildings and bridges stay standing, today's topic is super important. So we're going to dive into the world of steel compression members, and more specifically we're going to explore how each fail under axial load. Now I know failure mode might sound a bit scary, but understanding why and how columns fail is actually a huge part of designing safe structures. So in this video, what we're going to cover is what axial compression actually means, the four main failure modes you need to worry about, what factors influence these modes, and how this all ties into real-world design, especially in the context of S4100, which is the steel structures design code in Australia. Okay, so let's start right at the beginning. What exactly is a steel compression member that's axially loaded? Basically, it's any structural member like a column, a post, or a strut where the load being applied straight along its central axis. So what are these failure modes? So when a steel member is under axial compression, there are really four ways in which it can fail. Each one depends on different factors, and understanding them is crucial. Here are the four main failure modes: compressive yielding, also known as squashing; local buckling, where the individual plates buckle before the whole thing fails; elastic buckling, also known as Euler buckling; and inelastic buckling, which is more like what we see in real life. And out of all these, the one that actually controls how the member fails, so the governing case, depends on things like geometry of the section, how slender the member is, how it's supported, and of course any imperfections or residual stress that might be present. So let's break them down one by one. The first one is compression yielding or squashing. So this kind of failure happens when the column is short and thick, like super stocky. In this case, the member doesn't have room to buckle, and instead it kind of just gets crushed straight down under the load. It's like pressing a stubby cylinder of Play-Doh between your palms. It just squishes. Now, the load at which this happens is called the squash load, and it's calculated using the formula AN times Fy, AN being the net cross-section area, and this is basically the cross-section of the cross-section, so the whole area of the cross-section minus any holes, so bolt holes or cutouts that you might have in your section, and then Fy is the yield strength of the steel that you're using, so it could be 250 MPa, 300 MPa, 350, 400, etc. If your column doesn't really have bolt holes or cutouts, you might just use the cross-section area instead, AG. This kind of failure usually happens if the column slenderness ratio, that is L divided by R, is less than 25. This is essentially how we quantify what a stocky column is. So L is the length of the column, and then R is the radius of gyration, which is the square root of moment of inertia divided by area. Next up, we've got local buckling. Now this one's a little bit more nuanced, but super important. Even if your whole column doesn't buckle, individual parts of it can. Steel sections, especially open section like beams or channels, are made up of flat plates like flanges and webs. And if any of those elements are thin enough compared to their width, they can buckle on their own. So picture ripples forming on the web of an I-beam, or the flange starting to wrinkle. That's local buckling. It usually happens before the whole section fails, and it reduces the amount of load the member can carry. To account for this, Design standards like AS4100 introduce a form factor, KF, to reduce the squash load if local buckling is likely. So it's a reduction factor. If all the elements are nice and thick, like compact sections, you're most likely going to get a KF factor that's close to 1. That means there's no reduction in the squash load to account for local buckling. But if some elements are slender, the KF drops below 1, and this reduces the section capacity. Something to keep in mind is you need to check every single part of a compression member, like the flanges, the web, or any thin plate elements, because the whole cross section is under compressive force. That means everything is being squeezed together and not just a portion of it. This is different to members in bending, because in bending situations, only one side of the section is in compression and the other side is in tension. So in those cases, we typically only worry about the side that's being compressed. Now let's move into a bit of more theoretical territory, if you will. So elastic buckling, also known as Euler buckling. This is the classical failure mode we learn about early in engineering. I mean, a long slender column, something tall and thin with thin ends. As you slowly increase the axial load, the column stays straight for a while and then suddenly it bows out to the side and fails. That's Euler buckling. The critical load in this case is given by the following formula. The buckling load equals to pi square EI over L squared. This is a very, very common formula. Alright, now let's talk about what actually happens in real life, because columns are not perfect. Columns in the real world have all sorts of quirks. Maybe there's a slight curve in the member, which we call camber, or maybe the load isn't perfectly centered, it's eccentric, or maybe the steel has residual stress from the rolling or welding process. All that stuff lowers the capacity of the column compared to its theoretical value, like Euler predicts. This is what we call inelastic buckling. Now this is where AS4100 design comes into play. The code handles these real-world imperfections using things like effective length factors, which adjust for how the column is supported. I'm sure many of you would recognize the diagram with all sorts of effective length factors depending on how your column is supported on either end. So if you have fixed, it's 0.7. If it's pinned on both ends, it's 1. And if it's a cantilever, so fixed on one end but free on the other, you have a much greater effective length of 2.2. Next, you have the capacity reduction factor, which is 0.9 for compression. Reduction factors are common in standards. You'll see reduction factors for all sorts of design aspects, but in this case, for compression, we have 0.9. And then slenderness limits, which guides you on whether you're in the elastic or inelastic range. So at the end of the day, most columns are going to fail due to inelastic buckling, unless they're super short and stubby or have really thin plates that locally buckle first. So yeah, whether you're looking at a short chunky column or a tall slender one, knowing how they might fail is super important if you want to design something safe. I hope this breakdown helped clear things up, reduce confusion in compression members. And yeah, I'll see you in the next one. Thank you so much for watching.